Give it a whirl, Peter.
All right. Hopefully everybody can see my screen and hear me without an issue. So as Bob said, this is infrastructure for the DBA or data professional. I keep changing the title, and which is my own fault for not being consistent. But it is an introduction. Kind of the impetus to this session was being a consultant on site, talking to DBAs who had grown up in the developer side, or even some who had come from the business side, who were really good at the data side of things, but when we had to start having conversations about servers and connectivity, kind of were a little lost. So I wanted to create this session to help those folks catch up. And let's be very open and clear. This is about an hour-long session covering a whole lot of stuff. And we all know that we have peers in places that we work that have made entire careers out of each section of this document. So this is, as I say, an introduction, learning how to speak the language, not merely comprehensive. Who am I? I am a SQL Server database administrator, actually at 31 gifts. As I reviewed this deck this morning, I forgot to change that. I'm an intentionally accidental DBA. I grew up on the infrastructure side of the house, not surprisingly. My career path looks like an accidental DBA, except I did it on purpose. You can see my background. I'm the president of the local chapter here in Columbus, Ohio, co-organized SQL Saturday Columbus. I speak frequently at SQL Saturdays, including two that pass Lithopolis, which are Louisville and Indianapolis, which are coming up in August. And I am one of those folks who was fortunate enough to be selected, actually to do the expanded version of this session for Past Summit. So think about what these all have in common. And there are a lot of things, let's be honest, they all have in common. So there's a cell phone, a tablet, a laptop, a desktop, a server, and even a router. Yeah, they're all made out of plastic for the most part. Yeah, they all use power. But the thing I'm really driving at is that they have a CPU in them. And that CPU is attached to a motherboard. What's CPU? It's the central processing unit. It's the piece of hardware, the piece of silicon, or pieces of silicon, that process all the instructions we send through. When we send queries, when SQL Server runs the compiled code to build a query plan, when Windows does things, the CPU ends up being involved in all of that. You can see here on the picture of this motherboard, to the left of the picture are some expansion slots. This is where network cards go, where if this were a desktop PC, that high-end video card that you so dearly love to play video games on would go. There are other supporting components over there. If you look to the right, you see two identical sockets. Those are the CPU sockets. That's where those central processing units go. You'll notice that there are two identical banks of 3 blue and 1 black socket. That's where the memory goes. And in the case of a multi-socket device, like this motherboard is, like probably most of your servers are, each of those memory banks is directly attached via the bus on the motherboard to the to a processor. Sorry, I want to make sure that nobody was trying to get my attention in the chat that they couldn't hear me. So they're each attached to a bank of memory directly to the processor, which means the processor has extremely fast access to the memory. This configuration is what we call NUMA, or non-uniform memory access, because each processor does not have direct access to all of the memory. Each processor does have indirect access, and that is a very expensive operation in terms of computing cost. So non-uniform memory access, as I said, is NUMA, and kind of from a diagram perspective looks like this. You can see CPU with 4 cores, CPU with 4 cores, memory bank, and this is that really expensive bridge to cross. Having grown up on the East Coast, I sometimes, make the joke that it's like getting out of New Jersey. You have to pay no matter which way you go. For those of you who are in New Jersey, sorry. But that's really what NUMA boils down to in a very simple way. Yes, this can really affect how our queries run. And from an HADR perspective, NUMA is one of those places where we want the CPU to match across the hardware. If you're running in a virtual world, it becomes a little less impactful as long as you're following virtual server best practice to build your NUMA nodes and then set your max stop in your virtual machines to the lowest size of a NUMA node across your virtual ARM, because then it doesn't matter what host your machine ends up on. If you are in a physical world, which I understand is getting less and less, though for me, my primary servers run on physical boxes. They're not virtualized. It becomes important from a NUMA perspective that the cores per socket match. It's because you could potentially run into performance issues and getting sockets lined up. Microsoft's rules for max degree of parallelism have changed. It's okay to go to 16 for that setting now. So if I've got a 2-socket server with 16 cores in a socket, and I set my max stop to 16, that's great. Until I have to fail over to the other node that also has 32 cores, but it's 4 sockets of 8 cores in each processor. That can cause us some issues, of course. So we want to make sure that, to the extent we can control it, from an HADR perspective, we're filing over like to like whenever possible in terms of CPU. The memory density, we really would like the memory density to match. It is less critical, at least in my opinion, than the cores matching. There are some configurations where if you get out to the last rank of memory, where that last bank can be a little bit slower. So if you push down on one side and the other, you could have an issue. But before we get too hung up on exact match of hardware, slow but working is better than down and out of business. So you're much better off having a non-perfect HADR situation than none at all. Before I dive into storage, any questions at this point? All right, I will take the silence as a no. Obviously, after we have processor, memory, and of course, network card and all the other supporting hardware, we've got to store that data somewhere. If you're old school, you could have local storage where you have the disk controller in the server. The physical disks are in the server. Ideally, they're configured at a server level. Yes, you can configure the RAID levels at a software level, but they do not perform as well as if you configure them with an actual array controller and set up your redundant array of inexpensive disks that way. I've listed here the most common types of RAID. RAID 0 is striping with no parity or single disk. It gives you absolutely no redundancy. RAID 1 is a mirror, so you're going to pay a write penalty on that because it's got to write everything twice, but you are redundant. A couple of downsides. RAID 1 If you have a 1 terabyte disk and a 2 terabyte disk and mirror them, you only get 1 terabyte. You can't use, to the best of my experience, that other terabyte or that 2 terabyte disk. Moving to RAID 5, striping with parity. You have to have 3 physical disks for this. There is a write penalty for this configuration, but you do get a little bit of read performance. This is still a very common configuration. As I talk to DBAs at various SQL Saturdays and other events, as I talk to storage folks, the storage folks want to push RAID 5, and it doesn't necessarily make sense for what we do as data professionals. If you're in a read-only situation, sure, it might make some sense. But if it's an OLTP database, probably not. But it is highly redundant. You do lose, from a storage perspective, 1 disk. So whatever the capacity of that 1 disk is, you lose it. So if you have 3 2 terabyte disks, you have a 4 terabyte array, not a 6 terabyte array. But it will survive the failure of one of those disks. 2 disks fail, doesn't matter how big the array is, you have some issues. RAID 10 is a mirror of stripes. This can also be referred to, or some people will say it as RAID 1+0. So we have multiple disks that are striped, and then those stripes are mirrored. So it provides a nice degree of resilience. It requires, as you may guess, a minimum of 4 disks, and yeah, you lose 2 of them. However, you do not pay a write penalty for this, and there's no read penalty. You get plenty of performance out of it. And those read and write penalties are largely relative to spinning disk. It's been long enough since I've set up anything with RAID. I haven't really considered the idea of a RAID in local storage around an SSD. So I'd have to look into that before somebody asks that question. There is one other thing that I really should add here, which is what's called a JBOD, just a bunch of disks, which we could configure as local storage, and it's exactly what it sounds like. There's no redundancy. It is all of those disks, and they perform at the speed of the individual disk. I know people who I trust tremendously about this performance who use it. They monitor it heavily and have some very high degrees of rigor around when they change disks and how they monitor things, because there is no redundancy to the disk, but they've got it, stoked and really screaming for performance. And the person I've talked to most about this is really performance bound that way and uses it effectively. So it can be done, just be very much aware of it. We all know that locally attached storage is a bigger risk from an HADR perspective because it's locally attached. It becomes another thing we can add to the list of single points of failure. So we can look at some additional attached server storage types. We could do the external or physical server, just a chassis that holds a bunch of disks to augment our local storage. It's going to behave in some ways like local storage in terms of RAID levels or JBOD. Typically, it's used with traditional rack mount and tower servers, not really blades, which for purposes of this conversation, we'll define as non-traditional. It requires a physical connection to that server box. It doesn't add a ton of additional redundancy. It does add some nice expansion capabilities, because clearly in a standard tower or rack mount server, there's physical limitations on how many drives we can put in there. There's physical limitations, of course, on our next 2 candidates to talk about network attached storage and storage attached networks, NAS and SAN. But they are able to be expanded via shelves, and you can add additional disks to them at the enterprise level. Network attached storage is connected via NAS head or NAS server. It can be directly attached to the network using some storage protocols over Ethernet, most notably iSCSI. Server connects to the disk array. Typically, we'll use this with both blade or traditional servers. Depending on some network configuration issues or overall performance of the network, we can see some additional latency to this type of storage, and depending on the vendor of the storage, depending on how that's configured, it may or may not cause latency problems. Typically, this is not going to be your fastest storage, even with SSDs, because the intermediary connection could slow some things down. If storage detached networks, or SANs, which I'm sure most of us have, they connect to storage via a host bus adapter most typically, although they can do iSCSI over the LAN. That host bus adapter typically will do what's called fiber channel. It behaves, particularly as fiber channel connections, a lot more like directly attached onboard storage for either a blade or a traditional server. However, in fiber channel in particular, that fiber network, which is separate from your data network, will run at the speed of the single slowest component across the entire matrix. It doesn't matter if you're actually using that. If it's plugged in and it's 2 gigabit connection and everything else is 16, you're running your fiber at 2. This is an obvious problem, but if you don't know that that's the problem, it can be a little bit tenuous to figure out. With all storage, you will talk to SAN administrators and storage admins, and they will want to talk about IOPS, which are a wonderful thing. IOPS are input-output operations per second. We want to see big numbers there in terms of that bandwidth. We also are worried about latency. For those who are on the call that are in the United States, you've probably all been to a large city. You're all familiar with interstate highways. Bandwidth is how wide that highway is, how many lanes. You're very well aware, unless perhaps you live in Los Angeles, that there's a significant difference between the traffic at 2 o'clock in the morning on a Sunday and 5 p.m. on a Monday. That difference is going to affect how long it takes to get from the exit you get on at to the exit you get off at. That time is your latency on the highway. And it can be affected by bandwidth, but it's also affected by utilization. So latency is a key metric as we talk about the performance of storage. In all of these cases, all of the types of storage can, depending on the amount of money your employer is willing to spend, be a single point of failure. So be aware of that. Even if you have a highly redundant SQL configuration at the server level, you need to make sure your storage is equally redundant. Do we have any questions about storage? All right. Oh, local storage interfaces. This comes up old school SATA, or if you're really old school, IDE, which I didn't even mention on here. It's the way we typically attach hard drives and spinning disks or SSD to our servers or our desktop machines or our laptops. And with current standards, I believe it's 3.4 is the current standard of SATA. We can get up to 6 gigabits per second in transfer rate, which isn't so bad. NVMe or non-volatile memory express is a controller interface that works through the PCIe, the PCI Express channel, And it was specifically developed for SSD traffic. It allows us to get more performance out of those SSD drives as long as the interface is correct. We're starting to see NVRAMs, NVRAM, which was originally kind of like a flash drive, and moving into NVDIMMs where we have storage on RAM chips, order of magnitude faster than even NVMe. And capacities are still running a little small. And of course, since it's relatively new technology, capacity is tiny, price tag is not so tiny. Pardon me. A caveat as we look at this virtualization slide. When I say virtualization, I'm really and incorrectly thinking that that word is interchangeable with VMware, because it runs about 75-to-1 VMware versus Hyper-V in production environments from the consultants and folks I've talked to. Almost all SQL Server workloads can be virtualized, with the huge caveat of the hardware has to be the right hardware in the VM farm, and it's got to be properly configured, both the hardware and the VMs. If you're using VMware, there is a fantastic 70-something page document on how to build a highly performing SQL Server in VMware out on their website. And last I looked at it, it was updated in November of 2018. It may have been updated since then, but I don't know. And it is a document that I trust, and the fact that it comes with the VMware label on it and the VMware logo may help in some environments where the VM admins want to talk only about the documentation that comes from the vendor. What's virtualization really do? It creates an abstraction layer between Windows Server, or really any server platform, and the hardware. So the OS, Windows or Linux, talks to the virtualization layer, and that server OS thinks, in air quotes, that it is talking to actual hardware, which is how it's designed. In reality, it's talking to that virtualization layer, which then goes down and talks to the hardware and controls the access to that hardware, slices up when you get processor time, memory, and those kinds of things. When you virtualize a server, memory pressure may be an issue. There are a lot of inexperienced virtualization admins out there who will tell you if you're not using your memory, you have too much memory. VMware, at least, has documented that that is the memory counter that tells them that is completely untrue for SQL Server, because as we all know, SQL Server will take all the memory you give it and ask for more. You may have to, in some situations, set the minimum memory setting for SQL Server. I typically don't set that on physical boxes, and I typically don't set that in well-configured, well-managed VM environments, but you may have to. Of specific note to this particular group, virtualization is a viable part of a high availability solution. It is not the whole solution. In part because if a host in your VMware farm dies and that's running your SQL Server, you have to go through the time of the virtualization environment has to realize that host is down, move things over, bring them back up, and then SQL Server has to go into crash recovery and however long it takes to go through that based on in-flight transactions and all those things. If we've got a SQL Server level of HA in place, whether it be failover cluster instances, which in a virtualized environment can be a little challenging, though it's been a little bit since I've explicitly looked at that. I understand they are getting better at that. Or an availability group, it fails over and we've saved some time from an outage perspective. You've probably all read by now my comment here that says the backup approach can be an issue. There are some very popular products out there, one in particular that I'm thinking of, that is very commonly used to back up virtual machines. You must make sure it is properly configured to handle databases, because in a virtual environment, we don't want to freeze the I/O and take a snapshot of the virtual machine, including the databases. Otherwise, we have inconsistent databases and we need to recover from backup anyway. I've worked in places where I've negotiated with the virtualization team to say, hey, you back up the snapshot, you back up the machine state, exclude the drives that have the databases and transaction logs on them. I will take care of those with native backups. I've also worked with folks who configured the products correctly to take the backups with the particular backup software. As long as you can recover effectively and in the time allotment that you've been given from the business, either approach is fine. Just make sure it works. Oops. All right, apparently I lost my graphic. I'll have to look into that before I set up the slides to you guys. On virtualization versus containers. In virtualization, we're abstracting the hardware from the operating system. In containers, we are abstracting the applications and pieces, parts of the OS from the rest of the OS. So therefore, we need an underlying operating system that matches the operating system we're trying to use in the container, so we have all the parts we need. I would love to talk more about containers, but I admit I need to do a little more studying on them before I can do that. All right, I can't ignore the cloud. I don't want to ignore the cloud. And the cloud breaks down into roughly 3 types. There's infrastructure as a service, which is virtualized servers. You can replace almost all of your infrastructure except the things you absolutely have to have on site, such as actual network connectivity devices. It's really just VMs in somebody else's data center. It's the introduction to the cloud. It doesn't necessarily leverage all the power of the cloud. In my opinion, once you start to move your SQL servers into the platform as a service environment, where you're really moving back-end systems, not front-end systems, it can minimize the complexity of managing the infrastructure. And by minimize, I really mean it changes the complexity. There are different things you have to look at. It does not completely replace on-site infrastructure. There are some pieces you may still need on-site because you don't have all of the servers you need virtualized. And then there's software as a service, which is your productivity software. This is Office, this is Exchange, this is Power BI. And from a perspective of what do you use for what, if you're just doing infrastructure as a service, Amazon really does that pretty well in AWS because that's where it was born from, capacity in the data centers for that little website of theirs. I think Microsoft does, in Azure, does platform as a service better than AWS or Google Cloud. Google Cloud is probably the leader if you start talking, there's a contender if you start talking about machine learning and artificial intelligence, but I think as a whole, Microsoft has a better platform. And software as a service, from a productivity software perspective, Microsoft won that the day Office365.com went online, is the way I see it, because everybody, or almost everybody, uses Office, and it just moved to the cloud. There's no real, there's a little bit of difference, but that's not the focus of what we're talking about today. Yes, I use this old pizza as a service diagram just to give you an idea. Is it a perfect analog? No. Would I love to give credit to who built this first? Yes, I would. But I have no idea who it was because this thing has been through so many iterations and websites I've got no idea. The general gist here is that the things in blue, you're responsible for. The things in green, the providers responsible for. And you can see as we move through traditional on-premises all the way through software as a service, where our inflection points are, where we start to allow the vendor to take care of more things. And I know you're probably a DBA listening to this and you're going, I'm giving up control. I'm giving up control. That makes me nervous. That makes me uncomfortable. It's okay. You still control the things that are important, the access to your data. You still control performance tuning. In fact, those of you who have trouble getting developers to work with you on performance tuning queries, those of you who have trouble getting management to understand the importance of performance tuning, when you move it into a platform as a service environment, or even a software as a, or an infrastructure as a service environment, when you're having to pay for the processor and the memory and the disk resources you use, all of a sudden performance tuning becomes a whole lot bigger objective in their minds because there are dollars attached to it. When we can attach dollars to things, people tend to give it more attention. Now, that slide, shown a slightly different way, maybe something you're more interested to put in front of someone in management, kind of shows the overlap of software as a service, platform as a service, and infrastructure as a service. This came from a Microsoft Azure website, and given that Azure's in the name, there is some non-zero probability that that website has changed since the last time I looked at it, because it's been more than 5 minutes. So it's probably changed twice since the beginning of this call. Any questions to this point? All righty. We've talked about the server, we've talked about virtualization, we've talked about the cloud, but we haven't really talked about how to make all these things in our applications talk to each other. From a local area network perspective, or LAN, we've all heard this word before, or this acronym before. It's really all the computers that are connected in a limited area. It's your house, your school, your office building. There used to be this thing called a campus area network or a metropolitan area network when they were trying to get into, from a network perspective, all these labels. And we're good from that perspective. We don't have those anymore. Now they kind of all fit into the LAN area, or the LAN title, because on a campus, it's really just connected over a relatively short and contained distance. However, when we break off of that campus, when we break out of the office, when we break out of the school or the house, we get into the wide area network. It covers a lot of distance. Multiple data centers. The internet is, in fact, a wide area network. It is an interconnected set of many data centers, and I've way understated the number of many that go in that. If you're a larger corporation, you may have a wide area network, or a medium-sized corporation that has some small satellite offices. And you may be connecting over the internet. You may be connecting through some dedicated connections. All of that is an example of a wide area network. Across that wide area network, you may be using a VPN, particularly if you're connecting a satellite office, for instance, across the internet to the home office, or you're a remote worker. You're probably connecting in through a virtual private network. And it's basically a tunnel through the LAN. So it's a secure tunnel where there's a protocol wrapped in some encryption algorithm that is going through the general path, through the general traffic, and is connecting to a point on the other end where it's decrypted, and it's a private connection. Virtual local area networks, or VLANs. These you almost only ever hear about in office environments, although some of us on this call may have some VLANs at home. This is not specific to a hypervisor environment. This is really a segmentation of your existing local area network. Your storage, your network admins and your storage admins may have worked together to set this up for that network attached storage or that SAN storage that we talked about earlier, if the SAN's using iSCSI over Ethernet rather than fiber channel. You can partition the traffic. You can partition the security. So you can make sure that one channel on that VLAN can't talk to another. It allows us to do quality of service to shape the traffic as a network administrator, so we can give some higher priority to maybe that network attached storage traffic over the traffic out to YouTube. I've heard some folks talk in some ways about VLANs that makes it sound like they believe VLANs expand the bandwidth. That is not true. VLANs do not expand the bandwidth, they just slice up the existing bandwidth. Here in Ohio, I have a friend who is a network administrator at the state capitol building, and they quite literally use VLANs to segment the network into Republican network and Democrat network so that the traffic of the two parties does not intermingle, which I thought kind of funny, but not completely surprising. And again, slightly different context, but we're talking about bandwidth versus latency in terms of our network performance as well. And we've covered the maximum throughput versus the delay from input to outcome. Now, we have network devices, and these are some things we need to pay attention to. We have switches, which Cisco says switches build networks. I'm not going to argue with Cisco about how they define things when it comes to network. They are LAN-centric devices, which means they are internal. You might find them in wiring closets. If you work in an office, there's reasonable chance that you've got jacks in the wall that look like big fat phone jacks, which is effectively what they are, for your Ethernet cables from your desktop machine. Those are home run back to a wiring closet. There's probably a switch in there where those are consolidated and then connected back to the data center, or maybe to another switch and then back to the data center. Even if you're running wireless, these switches probably exist because those wireless access points run back to that switch and then move the data back into the network. So obviously they're connecting PCs to servers in the internet, connecting Wi-Fi access points. I just mentioned they're connecting servers to other servers. In the data center, we're almost always on physical Ethernet cabling through switches, servers to storage, and servers, of course, out to the internet. Speaking of the internet, there are these devices called firewalls. And they can be physical or software or virtual in a virtualization environment. And they're really used to block unauthorized access to a network or a network segment while facilitating outward communication. So you've probably got them at the edge of your network where it connects to the internet. You may have them between offices. You may have them between segments in your network if there is a secure segment to your network, if you're a PCI environment perhaps, or if you're a healthcare environment and there are certain devices that run a certain very secure piece of the network, there's probably a firewall between you and that. And there are several different types where we can just filter packets, which a packet is how the data transmits across the network. It just blocks packets that meet a certain requirement. Stateful inspection, where we're taking those packets we're blocking, but we're also seeing how they're related to each other. Make sure we do and don't block packets a little beyond just having a wall. And there are next-gen firewalls, which start to move into what we call intrusion detection systems, where they have intelligence and logic built into them that not only do they just drop packets that are attempting to make an intrusion to the network, they start to piece together that an intrusion attempt is actually happening, and then can send the appropriate alerts out. Now, when we connect all of these networks, we use routers, because routers connect networks. Again, I'm not going to argue with Cisco. It can be internal to the LAN. If we want to connect a couple of VLANs together, we may need a routing device. Now, there are two types of switches. There are layer 2 in the network model and layer 3 in the network model switches. Those layer 3 switches are also capable of doing routing. You see a lot of those configured today. And they are often used to connect different network segments together, such as those VLANs we talked about. Two of the key functions of a router: it discovers its neighbors, it knows who they can talk to and who they can talk to, who the individual router can talk to, and then who those networks can talk to, because it needs to use one of several different configurable protocols to forward packets on. In general, it is safe to say that the packets that are going back and forth as I speak are not necessarily taking the same path down the series of hops to wherever you are. They are, in fact, each packet may be going in a different direction, because at the time that packet goes across the network, there's a faster way to the next hop than there was for the previous packet or the next packet after it. So let's look at a picture. So this is kind of all of those network devices that we talked about. We have the switch here that's connecting the server and wireless access point. Okay, I disagree. I probably would have put the PDA over here, because I've yet to see one of those with an Ethernet port. You can think of this as a cell phone as well. Here we've got some laptops connecting to the wireless access point, and of course these wired PCs and workstations. The switch is connected to the firewall, which blocks traffic coming across the router unless it's authorized, and that's how we get out to the internet. It is completely possible to have a firewall, some devices, another firewall, and then the router. This is a picture with a whole lot more words on it, but it really just shows the fact that we can have multiple WAN connections within the same network without going over the internet. And this is what I was starting to explain before. The DMZ, or demilitarized zone, which is a safe zone from a connection perspective, where you can have a web server, for instance. You can connect from the internet, serve web pages, serve the things you need to connect to, and then that, there are certain packets limited by a firewall there on this internet edge. And then in here in the ASA, with the internet edge and the ASR and the ASA are Cisco specific terms, their product line. We would have another firewall, which is what this ASA is, in between the DMZ and our actual network, because we are probably going to want to restrict traffic even further than what we allow into that DMZ, that safe zone. And what I mean by safe is that zone is not safe. It is a zone that keeps the rest of our network safe. So network communication kind of works like this. There is a model developed called the OSI model, and it has these 7 layers that you can see in this picture. And as you're sending the packet, it goes down, pieces get added to the packet, comes across, and goes up, and it gets de-encapsulated on the receiving end and removes the pieces that are relevant to that particular layer, back off the packet till we get up to the application layer where the actual datagram is written or written on the sending side, read on the receive side. The reality is that TCP/IP is older than the OSI model. TCP/IP started with ARPANET in the Department of Defense in the 60s, so it's about 50 years old. And it is the beginnings of the internet. So for those who are old enough to understand this, Al Gore didn't actually invent the internet in 1994. If you don't get that joke, don't worry about it. So what we can see here is just a kind of comparison of the TCP/IP model, which is mostly what we use today, and the OSI model. And it shows where the overlaps are. The OSI model simply breaks some things out in a little more granular level. The TCP model is not so broken out. There's some applications, of course. You saw that application piece. In addition, to what we're going to see here, there are things like SMTP, which is email. There's FTP, HTTP. Of course, there's also DHCP, or Dynamic Host Configuration Protocol, which delivers TCP/IP address configuration information. The address, the subnet mask, the default gateway. You can deliver DNS information as to what the DNS servers are. And this is allocated to you by a lease that your computer will automatically renew for you, which is how you almost always, on the work network or on your home network where you're using DHCP, have the same IP address, although it is not guaranteed. Much like the table in SQL Server that doesn't have an index on it, order is not guaranteed. The IP address is not guaranteed. We can use DHCP to configure static addresses and manage those. If we enter into the DHCP console and put the MAC, or Media Access Control address, which is an address of a specific network interface card, into the server, when that network card broadcasts its MAC address to receive an IP address, the DHCP server will say, "Oh, I recognize you. You always will get this address." None of these addresses make any sense to us as humans, because other than Google's 8.8.8.8, or maybe Cloudflare's 1.1.1.1, do you know the address of your favorite websites? I don't. I always use real words. And that's where domain name services, or DNS, comes into things. DNS is effectively a phone book which converts names that we like to TCP/IP addresses that the computer likes. And the reality is the computer actually converts those TCP/IP addresses into binary strings, because computers like ones and zeros. The two we really need to be most familiar with here are A records, or address records, which links the records to a name, or canonical names, which are reference and redirection records. Now, it is very important to realize that depending on your disaster recovery and HA environments, you may have to change server names. If you're using log shipping, transaction, either type of replication, or old school mirroring, you would have to change the name of the server. Obviously, if you're using a failover cluster instance or an availability group and connecting to the listener or the cluster name, you're just going to go and continue to connect to that if you fail over. You can use a DNS record to point to a server name, to an instance name, in fact, and all the way down to not just the server and the name, but the named instance as well with it. So you can always go to the same thing. And that means that if you have to fail over, or if you just are doing an upgrade of the hardware or the database server itself, however you're doing that, you're building a new VM for it, and you don't want to go through the pain of redeploying an application and its connection strings, you can use a CNAME, mechanical name, in DNS to point to that instance, which then will allow you to just wait for DNS to be reconfigured or flushed on the DNS cache to be flushed on a particular endpoint, and it will make that connection. And we can force that if we need to. I note the MX record here, the mail exchanger, because it identifies anything that that points to as a mail server. So when you go in and configure database mail and then you have the smtp.company.com, that's a mail exchange record. As I said, TCP/IP was born out of the Department of Defense in the late 60s. Went into IP version 4, went into production in 1983 in ARPANET. It is a connectionless protocol, which means it does not continually have an end-to-end open connection. It sends the packet and waits for an acknowledgement. In TCP, in IP, TCP does not do the acknowledgement. That 2 to the 32nd addresses. We're out of addresses, folks. We're fortunate that a lot of companies are using firewalls and edge devices that do something called network address translation, or NAT, which allows us to use a whole lot of internal non-routable addresses, that 10 dot network you see in the office, that 192.168 that you see at home. Those are not routable on the internet. But through network address translation, we can use those on the internet, or we can use those to connect to the internet and have inbound connections as necessary and allowed. This is your classic, dot, 4 octets with dots between them notation that you're used to seeing all over the place. I've referenced the 8.8.8.8 and 192.168.1.1. Yes, I probably just said the default gateway address of most of your routers. The default gateway, by the way, is when internal routing fails, it says go that way. And it's the default. When in doubt, go here. IPv6 is not interoperable with IPv4 directly. And that has slowed its deployment, in my opinion. Modern Windows operating systems default to having TCP or IPv6 enabled, which is perfectly fine. It has a ridiculous number of addresses, and it's 8 groups of 4 hexadecimal digits. So not only does it have more groups, it has more opportunities in the group to use place values. Obviously, the reason we're out of IPv4 addresses because we all have, 1 or 2 cell phones, a tablet, a couple of laptops, all those things. They're using those IP addresses and connecting to the internet that way. I need to get through this here. Wired versus radios. Pros of wires. Generally, they're more secure. And tier by tier, they're higher speed. They're better for data centers. They lack flexibility because you got to put them in walls. And if you got to put them in walls, that means they cost more. The radios on the wireless side are more flexible. You can do BIOD, relatively low cost of installation because you get a whole lot of connectivity out of one access point. But the tier by tier speeds are slower. Because it is an open connection, meaning that somebody can be a man in the middle with a radio, the right type of radio. There's some security weaknesses, and as we're all well aware, they're susceptible to certain kinds of interference. I think we've all heard of Active Directory. It's Microsoft's implementation of the lightweight directory access protocol, and it's a hierarchical database. So yes, it is a database. Yes, it has a query language. No, it's not standard SQL. It's organized by organizational units. My personal advice is to segment your SQL servers into their own OU, separate out the service accounts away from regular user accounts. And this is because Active Directory allows us to do certain sets of settings to be what's called group policy. And if we have those things segmented, if we have those user accounts segmented out, we have those servers segmented out, we can take the time to apply the specific settings we need to all those accounts via group policy. Things like power management, things like block pages in memory, things, whatever settings you need that are specific to SQL Server in your environment. In Active Directory, we want to think about managed service accounts. They have complex passwords that are only known to your computer in Active Directory, and they change every 30 days automatically without requiring downtime, which is great if you have a password change policy. They're managed by those lovely SPNs. They are computer specific. And once you have Windows Server 2008 R2 with that Active Directory functional level, you can use a managed service account. And with, I believe it's with SQL Server 2008 R2, which is, please later today take a moment of silence, officially out of support. So SQL Server 2012, managed service accounts work fine. There are these things called group managed service accounts, which are not computer specific, and you can therefore use them on multiple hosts. They are officially supported starting with SQL Server 2016 and beyond. These are wonderful for failover cluster instances, so you can have that one managed service account on all of the nodes of the cluster and benefit from those password changes. And nobody knows the password because you don't need to know it. But you can't do it unless you've got SQL Server 2016. Yes, you can extend it to the cloud, both Azure and Web Services when we're talking about, or Amazon Web Service when we're talking about Active Directory. It's actually Azure Active Directory now. You may hear Active Directory Federation Services, which is the predecessor to Azure Active Directory, which is a cohort for single sign-on of Azure Active Directory, and it does work across all three types. So you can use your groups, whether they're in infrastructure service, platform as a service, or software as a service to manage things, manage access, all those wonderful things. If you're using Windows Server, the one thing that that Microsoft is consistently insistent on is the default setting for TCP chimney offload, which is a NIC-based setting. You want to disable it. Depending on the version you're looking at, it can be set by default to auto, it can be set by default to on, or it can be set by default to off. And Microsoft seems to keep changing that, so I would always check it. It's really designed for short-lived connections, but not the connections that we use typically see in SQL Server, and that can cause us some issues. You're familiar with the local policies of block pages in memory and perform volume maintenance. If you want to see the group policies you have, in fact, there's group policies we talked about from Active Directory, and an administrative command prompt, just do gpresult/r. And I would be remiss if I didn't mention antivirus. Microsoft has a great site that tells you what the antivirus exceptions should be set to for all of their products, including, of course, SQL Server. And yes, there are valid arguments on both sides of using antivirus on your SQL Server. The more and more I hear about ransomware, the more and more I'm leaning to antivirus on the SQL Server. But there are valid arguments in both directions of that. And that's really all I need to mention about AV. Does anybody have any questions as we're finishing up? All right, I will take that as a no. Bob?
I guess silence means approval. All right. Well, thank you very much, Peter, for taking the time to present today. Thank you to everyone who came out to watch the webinar. We will have the video of this posted up on the YouTube page within hopefully a day or two, and keep an eye on your emails for announcements about our next meeting. Again, thank you all very much. And
thank you, and thanks for having me, Bob.
All right, no problem. Have a good one, everybody.
Bye-bye.